For decades, scientists believed the universe was vast but ultimately measurable. About 14 billion light-years in every direction, containing a few 100 billion galaxies scattered through space. That picture felt enormous, yet measurable. Then the James Webb Space Telescope turned its mirrors toward what appeared to be empty darkness, and that certainty collapsed. Webb revealed an observable universe nearly 93 billion light-years across, packed with stars hiding where nothing was supposed to exist. It found fully formed galaxies just 300 million years after the Big Bang, black holes growing faster than physics predicted, and structures far too large for their age. But the most unsettling revelation isn't how far Webb can see. It's what these discoveries imply about what lies beyond our cosmic horizon, and why most of the universe may be forever unreachable. If you're ready, hit that like button, subscribe, and let's discover together what James Webb found this time. To understand what the James Webb Space Telescope is truly revealing, we first have to abandon the idea that space is something we simply look across. In the universe, distance and time are inseparable. Light moves at a constant speed, about 186,000 miles per second. It is the fastest thing that exists, fast enough to circle Earth more than 7 times in a single second. Yet even at that speed, distance immediately turns into delay. The farther light travels, the older the image it carries when it finally arrives. When you look at something a mile away, you see it as it was a few millionths of a second ago. When you look at the moon, you see it 8 seconds in the past. When you look at the sun, you are not seeing it as it is now, but as it was 8 minutes ago. This sky is not a live display of reality. It is a stream of information arriving late. These delays are so small that we never notice them in daily life. Our brains treat the world as immediate and continuous. But as our gaze moves outward, the delays grow, and eventually they reshape how the universe itself must be understood. The nearest star beyond our sun appears to us as it was more than 4 years ago. The centre of the Milky Way is seen as it existed 26,000 years in the past. And when we look beyond our galaxy, into the vast spaces between stars, we are no longer observing the universe as it exists today. We are reading earlier chapters of a story already billions of years old. The night sky, then, is not a snapshot. It is an archive. Every point of light carries a timestamp. Every photon is a messenger from a different moment in cosmic history. The farther away its source, the older the message it brings. The challenge is that the universe does not preserve these messages unchanged. As the universe expands, space itself stretches. And when space stretches, it stretches the light travelling through it. Wavelengths grow longer. Energetic blue and ultraviolet light shifts toward red, then slips into infrared. This effect, known as redshift, is not just a visual change. It is a record of how much the universe has expanded since the light began its journey. Redshift acts like a cosmic clock. The more stretched the light, the longer it has been travelling, and the earlier in the universe's history it was emitted. For decades, astronomers relied on telescopes optimised for visible and ultraviolet light, the narrow slice of the spectrum human eyes evolved to see. Instruments like Hubble transformed our understanding of nearby galaxies, star-forming regions, and the large-scale structure of the cosmos. But as scientists tried to look farther back in time, the universe began to fade. Not because it wasn't there, because its light had changed. Ancient galaxies did not disappear. Their light simply drifted beyond the range those telescopes could detect. The James Webb Space Telescope was built to follow that missing light. Its mirror spans more than 21 feet and is coated with a microscopically thin layer of gold, chosen because gold reflects infrared light with extraordinary efficiency. Webb does not orbit Earth. It operates nearly 1 million miles away, at a stable gravitational point where it can remain pointed steadily, shielded from heat and glare. That distance allows Webb to stay extremely cold, and that cold is essential. Infrared light is closely tied to heat, and a warm telescope would drown out the faint signals it is trying to detect. Webb had to become quiet enough to hear the universe whisper. When Webb stares into a region of sky that appears completely black to our eyes, it is not searching for emptiness, it is waiting. Waiting for photons that have been stretched almost to invisibility by billions of years of cosmic expansion. Those photons arrive slowly, sometimes one by one. Webb may stare at the same patch of sky for many hours, even days, patiently collecting light that has crossed nearly the entire observable universe. And what it finds there is not a quiet, tentative cosmos just beginning to form. It finds a universe that is already busy. Some of the galaxies Webb has detected formed when the universe was only about 300 million years old, less than 3% of its current age. To grasp how early that is, imagine compressing the entire history of the universe into a single year. These galaxies would appear on January 2nd. According to long-standing models, this era, often called cosmic dawn, should have been relatively dim. The first stars were expected to ignite slowly. Early galaxies were predicted to be small, fragile collections of gas and stars, taking hundreds of millions of years to grow into anything substantial. But Webb saw galaxies that were already bright, already massive, and already forming stars at intense rates. Some were luminous enough that even if they were much farther away, Webb could still detect them. That brightness matters. Bright galaxies require large populations of stars, and stars do more than shine. Inside their cores, they forge heavier elements like carbon and oxygen, elements that did not exist in the universe's earliest moments. Those elements are released only when stars die. When Webb detects heavy elements in such young galaxies, it is seeing evidence that earlier generations of stars must have already formed, lived, and ended their lives. The universe had already gone through multiple cycles of creation and destruction far sooner than expected. The cosmic clock was being pushed backward. The universe did not slowly ease into complexity. It accelerated toward it. There is also something quietly humbling about the act of observing this ancient light. Webb does not capture these images instantly. It gathers photons that have been travelling for more than 13 billion years, photons that began their journey when the universe was young and unfamiliar. When that light started moving, Earth did not exist. The sun had not formed. The Milky Way was still assembling itself from clouds of gas and dark matter. Oceans, life, civilizations, every chapter of human history unfolded while those photons were already on their way. By the time Webb detects them, we are not witnessing events happening now. We are witnessing moments that happened once, long ago, preserved in transit and never to be repeated in quite the same way. This is why astronomers say James Webb doesn't just look far away, it looks backward through time. Distance becomes a timeline. Nearby objects show the universe closer to the present. Distant objects reveal earlier and earlier stages of cosmic history. Yet even Webb's extraordinary vision has a fundamental limit. No telescope, no matter how powerful, can see beyond a boundary set by physics itself. That boundary is defined by how far light has been able to travel since the universe began. It is called the observable universe, a vast sphere centered on us, with a radius of about 46.5 billion light-years. Webb is now pushing observations closer to that boundary than ever before, detecting galaxies at distances once thought unreachable. But even Webb cannot see beyond the cosmic horizon. And this is where the realization becomes unsettling. Space does not stop at the edge of what we can observe. Beyond that horizon, galaxies still exist. Stars still ignite and die. Black holes still merge. Entire cosmic histories unfold in regions forever hidden from us. Not because technology is lacking, but because space itself is expanding too fast. James Webb has not only shown us how far our vision can reach, it has shown us how much of the universe lies permanently beyond it. And as we take in what Webb has revealed within our observable bubble, the early brightness, the rapid formation of structure, the sheer abundance of galaxies, a deeper question begins to emerge. If this much exists in the small fraction of the universe we can see, what does that say about the true scale of everything that exists beyond our view? For most of modern astronomy, the early universe was imagined as a quiet and fragile place. After the Big Bang, space expanded rapidly, temperatures dropped, and matter spread out almost evenly in every direction. Tiny fluctuations existed, regions that were slightly denser than others, but gravity was expected to work slowly, patiently pulling matter together over vast spans of time. In this picture, the first stars ignited reluctantly. Gas needed time to cool. Dark matter halos needed time to grow. Galaxies, when they finally appeared, were expected to be small and faint, delicate structures that would take hundreds of millions of years to mature into anything substantial. The universe, according to this model, learned to walk before it learned to run. That expectation shaped decades of theory. So when the James Webb Space Telescope began surveying the early universe, astronomers anticipated scarcity. A few primitive galaxies here and there, dim objects clinging to existence in a young cosmos still finding its footing. Instead, Webb found crowds. Again and again, bright galaxies appeared in eras that should have been nearly empty. These were not faint sparks barely holding together. They were already busy systems, producing stars at rates comparable to or exceeding those of much later galaxies. The surprise wasn't the discovery of one strange object, it was the pattern. Within the universe's first 500 million years, Webb detected galaxies emitting enormous amounts of light. Some contained hundreds of millions, even billions, of stellar masses worth of material. That amount of mass should have required far more time to assemble than the universe had available. Gravity is powerful, but it is not fast. Gas must lose energy before it can collapse. Dark matter halos must accumulate enough mass to trap ordinary matter. Stars take millions of years to form, and those stars must live and die to enrich their surroundings with heavier elements. Each step imposes a minimum timescale. Compress the sequence too much, and the physics stops working. And yet, the galaxies were already there. One of the most unsettling aspects of these discoveries was not just the size or brightness of early galaxies, but their chemical maturity. Webb's spectroscopic measurements revealed signatures of carbon, oxygen, and nitrogen, elements that do not exist in meaningful quantities immediately after the Big Bang. These elements are forged inside stars. Their presence in such young galaxies means something unavoidable. At least one earlier generation of stars must have already formed, burned through their fuel and ended their lives, spreading heavy elements into space. All within the universe's first few hundred million years, the cosmic clock was being pushed backward. To understand why this troubled astronomers so deeply, it helps to think of galaxy formation like building a city. You cannot construct skyscrapers before roads exist. You cannot pour concrete before steel is produced. Each stage depends on the one before it. The early universe was supposed to be laying foundations. Webb found finished buildings. This growing mismatch between theory and observation became known as the too much light too early problem. When astronomers calculated how much total light galaxies should produce during the universe's first billion years, their predictions fell short. Webb's observations exceeded those predictions by factors of 2, 5, and sometimes even 10. That kind of discrepancy is not a rounding error, it is a signal. Scientists did what they always do when faced with something this unsettling. They questioned the measurements, they rechecked the instruments, they reanalyzed the data. They asked whether dust, gravitational lensing, or observational bias could be making galaxies appear brighter or more massive than they truly were. Again and again, the result held. The early universe was not dim, it was luminous. Some of these early galaxies were so massive that researchers briefly referred to them as universe breakers, objects whose existence seemed to violate the limits imposed by cosmology itself. According to standard models, galaxies of that size should not exist at those ages, not unless something fundamental about early cosmic evolution was misunderstood. At first, some astronomers hoped the masses were overestimated. Perhaps the light wasn't coming from stars alone. Perhaps supermassive black holes at galactic centers were contributing additional brightness, making galaxies appear larger than they really were. Further analysis showed that this explanation helped, but only partially. Yes, some early galaxies do host extremely active black holes, whose energy inflates their apparent brightness. Accounting for that reduced the most extreme discrepancies. But even after those corrections, the early universe still contained roughly twice as many massive galaxies as theory predicted. The tension eased. It did not disappear. This pattern repeated across multiple surveys. Webb looked in different directions at different regions of sky, using different instruments and wavelengths. Each time, the result was the same. The early universe was crowded. Galaxies formed quickly. Star formation proceeded with startling efficiency. This forced astronomers to reconsider a basic assumption: how efficiently the universe could turn gas into stars. In the modern universe, star formation is surprisingly inefficient. Most of the gas inside galaxies never becomes stars. It gets heated, stirred by turbulence, blown away by stellar winds, or disrupted by radiation. A massive molecular cloud may spend millions of years producing only a modest number of stars before dispersing. Early galaxies appear to have played by different rules. One possibility is that the early universe was simply denser. With matter packed more tightly together, gas clouds collided more often, triggering rapid collapse. Another idea is that the first stars formed from nearly pure hydrogen and helium, without heavier elements to complicate cooling processes. Under the right conditions, this simpler gas may have collapsed more directly than modern, metal-rich gas. Mergers likely played a role as well. In the early universe, galaxies were closer together, collisions were more frequent. When galaxies merge, gas is driven toward their centers, compressed to extreme densities, and ignites intense bursts of star formation. A galaxy could build much of its mass in short, violent episodes, rather than through slow, steady growth. Each of these ideas helps explain part of the picture. None fully resolves it. At the centers of many of these early galaxies lies another mystery entirely. Webb has identified supermassive black holes already in place when the universe was less than 500 million years old. Some of them weigh millions or even billions of times the mass of our Sun. According to conventional physics, that should not be possible. Black holes form when massive stars collapse. The resulting black hole may weigh tens of solar masses. From there, it can grow by consuming surrounding matter, but that growth is limited. As material falls in, it heats up and radiates energy, pushing back against further infall. Even under ideal conditions, building a billion solar mass black hole should take far longer than the early universe allowed. Yet Webb keeps finding them. This has forced astronomers to consider possibilities that once seemed extreme. Perhaps some black holes formed through the direct collapse of massive gas clouds, skipping the stellar stage entirely. Perhaps the first stars grew thousands of times more massive than modern stars, collapsing directly into large black holes. Perhaps black hole mergers were far more common in the dense early universe than we once assumed. None of these ideas has been confirmed. None can be ruled out. What makes this period so important is that these early galaxies and black holes shaped everything that followed. Their radiation transformed the universe, stripping electrons from hydrogen atoms during an era known as reionization. Their supernovae enriched space with heavy elements. Their gravity pulled matter into the first large-scale structures. If they formed earlier and more efficiently than expected, then the entire timeline of cosmic evolution shifts. And as Webb continues to look deeper, the pattern becomes harder to ignore. The universe did not wait patiently to become complex. It rushed. It assembled stars, galaxies, and black holes at a pace that challenges our best equations, which leads to an unavoidable realization. If the universe could build this much structure so quickly, then the scale of what exists today, after billions more years of growth, may be far larger than we ever imagined. And that realization becomes impossible to escape when Webb does something even more unsettling. It counts how many galaxies actually exist. For most of the 20th century, astronomers believed they had reached a reasonable answer to one of the biggest questions imaginable. How many galaxies exist in the universe? The method was simple in principle, even if challenging in practice. Point a powerful telescope at a tiny, seemingly empty patch of sky. Count every galaxy you can detect, and then scale that number up to cover the entire observable universe. When the Hubble Space Telescope performed its deepest observations, it revealed nearly 10,000 galaxies in a region of sky no larger than a grain of sand held at arm's length. That image was shocking at the time. From it, astronomers estimated that the universe contained a few 100 billion galaxies. The number was almost impossible to comprehend, and for years it stood. Then the James Webb Space Telescope looked at the same darkness. Where Hubble saw black gaps between galaxies, Webb saw faint infrared glows. Where Hubble detected smudges barely rising above the noise, Webb resolved structure. Regions that once felt empty suddenly revealed themselves as crowded, layered, and alive with distant systems that had been invisible before. This difference was not a failure of Hubble, it was a limitation of wavelength. As the universe expands, the light from distant galaxies stretches into the infrared. By the time that light reaches us, it no longer lives in the visible range that Hubble was designed to study. The galaxies were always there. Their light had simply slipped past our eyes. Webb was built to catch it. In one of its most ambitious observations, Webb surveyed a region of sky only slightly larger than 3 full moons placed side by side. For hundreds of hours, it collected more than 10,000 individual exposures, each one capturing faint infrared signals that had travelled across cosmic time. When those images were combined, the result was staggering. Nearly 800,000 distinct galaxies filled the frame. 800,000 galaxies in a patch of sky most people would dismiss as empty. To grasp the scale of that result, imagine printing the famous Hubble Ultra Deep Field on a standard sheet of paper. To show the Webb image at the same level of detail, the print would need to be more than 13 feet tall and 13 feet wide, a wall-sized mural of cosmic history. And every point of light in that mural is not a star. It is a galaxy. Each of those galaxies contains millions, billions, or even trillions of stars. Many host planetary systems. Many contain complex chemistry, dust, and heavy elements forged by generations of stars. The universe, it turns out, is not sparsely populated with isolated islands of matter drifting through darkness. It is densely packed, layered with structure at every scale. What makes this discovery even more powerful is that Webb did not simply count galaxies, it measured them. For each galaxy, astronomers can estimate its distance, its mass, its rate of star formation, and their approximate age. That allows scientists to reconstruct how galaxies changed over nearly the entire history of the universe, tracking growth from early cosmic dawn to the present day. And when they did that, a deeper pattern emerged. Galaxies are not scattered randomly through space, they cluster, They align. They trace invisible pathways. On the larger scales, the universe resembles a vast cosmic web, long filaments of matter stretching tens and hundreds of millions of light years, intersecting at dense nodes where galaxy clusters form, and separated by enormous voids where almost nothing exists. This structure had been predicted for decades, but Webb revealed it with unprecedented clarity. Many of the galaxies Webb detected were hidden behind dust that blocks visible light, but allows infrared wavelengths to pass through. Entire populations of dusty star-forming galaxies suddenly appeared, filling in gaps where earlier surveys saw emptiness. The cosmic web did not just become clearer, it became more crowded. This matters because the distribution of galaxies is not random decoration. It is a record of how the universe grew. Shortly after the Big Bang, matter was spread almost evenly throughout space, with tiny fluctuations in density imprinted during the universe's earliest moments. Regions that were slightly denser than average exerted slightly stronger gravity. Over time, matter flowed toward those regions, amplifying the differences. Gravity carved space into filaments and nodes, draining matter from surrounding regions and leaving behind vast voids. A useful analogy is rainfall over uneven terrain. Water drains into valleys, carving rivers and channels, while higher ground is left dry. Over time, a structured landscape emerges. The universe evolved in much the same way, except the flowing substance was matter itself. Webb's observations show that this process was already well underway surprisingly early in cosmic history. Filaments tens of millions of light-years long existed when the universe was only a few billion years old. Some structures were so large and so organized that they challenged expectations about how quickly matter could arrange itself. One striking example is a structure astronomers call the cosmic vine. It is a chain of at least 20 closely packed galaxies stretching more than 13 million light-years across. These galaxies existed when the universe was still young, yet the structure rivals much older formations in size. What makes the cosmic vine especially intriguing is not just its scale, but its state. Several of its largest galaxies have already stopped forming stars. They are quiescent, meaning they have exhausted or lost the gas needed to create new stars. This is unusual so early in cosmic history, when most galaxies are still actively forming stars. The implication is that environment matters. Galaxies in dense regions evolve differently than isolated ones. Interactions, mergers, and the harsh conditions of crowded space can accelerate a galaxy's life cycle, forcing it to grow rapidly and burn out early. And this is not an isolated case. Using Webb data, astronomers compiled the deepest and most comprehensive catalogue of galaxy groups ever assembled. They identified more than 1,600 galaxy groups and protoclusters spanning from about 12 billion years ago to just a few billion years ago. These groups represent the building blocks of today's massive galaxy clusters. By comparing groups at different distances, scientists can watch structure formation unfold over time. Early groups appear chaotic, with irregular galaxies forming stars at high rates. Later groups show more order. Galaxies become smoother, star formation slows, and gravity begins to dominate over turbulence and gas inflow. This continuous view across billions of years was simply not possible before Webb. Yet for all this density and organization, the universe is also defined by its emptiness. Between the filaments of the cosmic web lie vast voids, regions spanning tens to hundreds of millions of light-years that contain very few galaxies. These voids are not small gaps. They are the largest contiguous structures in the universe by volume. If you could place yourself at the center of one of these voids and look in any direction, you would see darkness stretching for tens of millions of light-years before encountering the nearest galaxy. Entire regions of space failed to accumulate matter simply because gravity pulled that matter elsewhere. Webb's deep field images capture this contrast vividly. In the same frame, dense clusters of galaxies appear alongside yawning black regions containing almost nothing. The universe is simultaneously crowded and empty, rich and sparse, structured and desolate depending on where you look. This brings us back to the numbers. If Webb's deep fields are representative, and multiple observations in different directions suggest they are, then the total number of galaxies in the observable universe may not be hundreds of billions, but trillions. For every galaxy we once thought existed, there may be 10 more hiding beyond what earlier telescopes could detect. That revision changes everything. More galaxies mean more stars mean more planets mean more opportunities for complexity to arise. The universe becomes not just larger in size, but richer in possibility. Yet even this staggering abundance exists only within the observable universe. Beyond that boundary, space continues, galaxies continue, structure continues. James Webb has shown us that even the portion of the universe we can see is vastly larger and more crowded than we believed. And that realization forces an even deeper question. If reality is this rich within our visible horizon, what does that say about the scale of everything we can never observe? At first glance, the universe seems easy to measure. The Big Bang happened about 13.8 billion years ago. Light travels at a fixed speed. So it feels natural to assume that the farthest objects we can see should be about 13.8 billion light-years away. For a long time, even scientists spoke about the universe as if that were true. But that intuition quietly breaks down the moment we take cosmic expansion seriously. The observable universe does not have a radius of 13.8 billion light-years. It has a radius of about 46.5 billion light-years, making its full diameter roughly 93 billion light-years. This is not speculation or artistic license. It is a measured result, supported by observations of cosmic expansion and the behavior of ancient light. The reason this number feels impossible is because it clashes with how we instinctively think about motion. Nothing can travel faster than light through space, and that rule still holds. No galaxy is racing through space at impossible speeds. No signal is breaking the cosmic speed limit. Instead, the universe has found a way to grow far larger without violating any laws of physics. It does this by stretching space itself. When we say distant galaxies are moving away from us, it is tempting to picture them flying outward like fragments from an explosion. That image is deeply misleading. On large scales, galaxies are not really moving through space at all. They're being carried apart as the space between them expands. A familiar analogy helps make this intuitive. Imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot moves farther away from every other dot. None of the dots are at the centre. None of them are moving across the surface under their own power. The surface itself is stretching, and the dots simply go along for the ride. The universe behaves in much the same way. When a distant galaxy emitted the light we detect today, it was far closer to us than it is now. Over billions of years, while that light was travelling toward Earth, the space between us and the galaxy expanded continuously. By the time the light finally arrived, the galaxy that emitted it had been carried tens of billions of light-years farther away. This is why we can observe galaxies whose light has been travelling for 13.5 billion years, even though their current distance is more than 46 billion light-years. Light is not simply crossing a fixed distance. It is moving through a distance that is growing while it travels. In effect, light has been running on a cosmic treadmill. Early in the universe's history, expansion was slower. Light made steady progress. As time passed, expansion accelerated, stretching distances faster and faster. Some photons managed to reach us because they started their journey early enough before the expansion rate became overwhelming. Others never will. This creates a boundary known as the cosmic horizon. The cosmic horizon is not a wall or an edge in space. There is no place where the universe suddenly stops. Instead, it is the limit of what can ever be observed from our location, given the finite age of the universe and the way space expands. Beyond that horizon, light simply cannot reach us, not because it lacks time, but because the space it must cross grows faster than light can traverse it. And this is where the universe becomes deeply unsettling. Space does not end at the cosmic horizon. We know this because the universe looks essentially the same in every direction we observe. The distribution of galaxies does not thin out toward an edge. The cosmic microwave background, the faint afterglow of the Big Bang, appears almost perfectly uniform across the entire sky. That smoothness would be impossible if space abruptly ended just beyond our view. So the universe extends beyond what we can see, but it does so in a way that permanently hides much of itself. Beyond 46.5 billion light-years, galaxies still exist. Stars still ignite and die. Black holes still merge. Entire cosmic histories unfold in regions that will never influence us and can never be influenced by us. No signal from those regions will ever reach Earth, not because our technology is inadequate, but because the structure of space-time itself prevents it. Even more unsettling, this boundary is not fixed. As time passes, the observable universe grows larger because light from more distant regions has had more time to reach us. The horizon creeps outward, but at the same time, cosmic expansion is accelerating, driven by dark energy. Space itself is stretching faster now than it did in the past. These two effects compete with one another. The result is a universe where some objects briefly become observable, only to later slip beyond reach forever. Galaxies we can see today are not guaranteed to remain visible indefinitely. Their light will continue to stretch, shifting into longer and longer wavelengths. Eventually, that light becomes so diluted and redshifted that no telescope could ever detect it. From our perspective, those galaxies will appear frozen at a particular moment in their history, slowly fading until they vanish completely. This is not a theoretical curiosity. It is a direct consequence of measured expansion rates. If the universe continues behaving as it does now, then in roughly 100 to 150 billion years, every galaxy outside our local gravitationally bound group will cross the cosmic horizon. Future observers would see a universe containing only a small cluster of nearby galaxies surrounded by darkness. The evidence of cosmic expansion, the cosmic microwave background, and the vast web of distant galaxies would be gone. They might never know that anything else ever existed. This leads to a profound shift in perspective. The observable universe is not the universe. It is simply the portion of the universe that happens to be observable from where we stand at this moment in cosmic time. Move to another galaxy, and the observable universe changes. Different galaxies enter view, others disappear beyond the horizon. Every location in space defines its own observable universe. This creates strange and counterintuitive situations. Two galaxies can both be observable from Earth, yet unable to observe each other. They may lie on opposite sides of our horizon. Light from both reaches us, but light from one cannot reach the other. From their perspectives, Earth itself may lie beyond their cosmic horizon. There is no privileged vantage point, no center, no location from which the entire universe can be seen. Every observer, no matter where they are, sits at the center of their own observable bubble. This is why the James Webb Space Telescope is so transformative. By pushing observations closer to the cosmic horizon than ever before, Webb forces us to confront the limits of what observation can achieve. When Webb detects galaxies at extreme redshifts, it is not just showing us ancient objects. It is showing us the boundary of causal connection. Those galaxies are no longer where their light began. Their current state, their later mergers, transformations, and possible destruction is unknowable to us. That information is still travelling through space, stretched and diluted by expansion, and in many cases will never arrive. What we see is not what is, it is what was. And even that view is incomplete. Beyond the observable horizon lies the unobservable universe, regions that may contain galaxies, clusters, and structures just as rich and complex as those we see. Some models suggest the universe may be infinite. Others propose it is finite but unimaginably large. Either way, the observable universe is almost certainly only a small fraction of the whole. James Webb has not revealed the edge of the universe. It has revealed that there is no accessible edge at all. And as this realization settles in, another question becomes unavoidable. If most of the universe is hidden by expansion, if vast regions of reality are permanently beyond reach, then something must be driving that expansion to accelerate. To understand that force, we have to confront the most dominant and most mysterious ingredient of the cosmos itself. For most of the 20th century, the story of cosmic expansion seemed straightforward. The universe began in the Big Bang, everything rushed outward, and gravity gradually worked to slow that expansion down. Astronomers debated whether the universe would expand forever or eventually collapse back in on itself, but the underlying assumption was the same in every scenario. Gravity was in control. That assumption did not survive contact with observation. In the late 1990s, astronomers studying distant stellar explosions noticed something deeply unsettling. These explosions, known as type Ia supernovae, shine with a remarkably consistent brightness. Because of that reliability, they act like cosmic mile markers. By comparing how bright a supernova appears to how bright it should be, scientists can calculate its distance. Combine that distance with how fast the host galaxy is receding, and the expansion history of the universe reveals itself. What those measurements showed was the opposite of what anyone expected. The universe was not slowing down, it was speeding up. Distant galaxies were farther away than they should have been if expansion were gradually easing under gravity's pull. Something was pushing space apart, not just preserving the expansion, but accelerating it. The farther back astronomers looked, the clearer the pattern became. Expansion had been gaining speed for billions of years. To account for this behavior, cosmology was forced to introduce a new ingredient: dark energy. Dark energy is not something we can see, touch, or directly detect. It does not emit light. It does not absorb radiation. It does not clump into stars, galaxies, or clouds. Its existence is inferred entirely from its effect on the universe's expansion, and that effect is overwhelming. Measurements now indicate that dark energy makes up roughly 68% of everything that exists. Ordinary matter, everything from galaxies and stars to planets and people, accounts for less than 5%. Dark matter makes up most of the rest. The universe we can see, the universe that feels solid and familiar, is a minor component of reality. What makes dark energy especially unsettling is how it behaves as the universe grows. Normal matter becomes diluted as space expands. Double the volume of space, and the density of matter drops by half. Radiation thins out even faster. Dark energy does not follow these rules. Its density remains constant even as the universe expands. As space grows larger, the total amount of dark energy increases. This creates a runaway effect. More space means more dark energy. More dark energy drives faster expansion. Faster expansion creates more space. Over billions of years, this feedback loop has shifted the balance of power in the universe. Early on, matter dominated. Gravity sculpted galaxies, stars, and the cosmic web. But as the universe expanded and matter spread thinner, dark energy quietly took over. About 5 billion years ago, it became the dominant influence on cosmic expansion. The James Webb Space Telescope does not detect dark energy directly, but it sees its fingerprints everywhere. The extreme stretching of ancient light, the immense size of the observable universe, and the way distant galaxies recede all reflect the influence of this invisible force. Without dark energy, the universe would be far smaller. The cosmic horizon would sit much closer. Vast regions we can see today would never have been observable at all. Dark energy does more than shape the present. It determines the universe's future. If dark energy remains constant as current observations suggest, then expansion will continue forever, accelerating as time passes. Galaxy clusters will remain gravitationally bound, but everything outside them will gradually slip beyond the cosmic horizon. Trillions of years from now, observers inside a galaxy like the Milky Way would see a lonely cosmos, filled with stars nearby but empty beyond. The universe would still exist, but it would look almost vacant. Yet this picture is complicated by one of the most serious unresolved problems in modern cosmology. A problem that James Webb has not erased, but instead made harder to ignore. When scientists measure how fast the universe is expanding today, they do not get one answer, they get two. One method looks deep into the past by studying the cosmic microwave background, the faint afterglow released when the universe was only about 380,000 years old. From the subtle patterns in that radiation, scientists infer an expansion rate of about 67 kilometers per second per megaparsec. The second method looks nearby. Astronomers measure distances to galaxies using Cepheid variable stars and Type Ia supernovae, then compare those distances to how fast the galaxies are receding. This approach consistently produces a higher value, around 73 kilometers per second per megaparsec. Both measurements are precise. Both have been repeated many times. Both have been scrutinized for errors. They do not agree. This discrepancy is known as the Hubble tension, and it represents one of the deepest cracks in our understanding of the universe. James Webb was expected to clarify the situation by providing cleaner, more accurate distance measurements. Instead, Webb confirmed the higher expansion rate measured in the nearby universe. The tension did not disappear. It sharpened. This leaves cosmology in an uncomfortable position. Either something is wrong with our measurements, something is wrong with our assumptions, or something fundamental is missing from our models of reality. One possibility is that dark energy is not constant after all. Its strength may have changed over cosmic time, altering the expansion rate in ways our current models do not capture. Another possibility is that unknown physics affects how light travels across enormous distances, subtly biasing measurements. Or the early universe itself may have behaved differently than we assume, imprinting expansion behavior that evolves in unexpected ways. Each possibility carries profound consequences. The expansion rate determines the universe's age, its size, and its ultimate fate. If we are misunderstanding it, then many conclusions drawn from decades of cosmological research may need revision. The problem is not cosmetic. It cuts to the foundation of how we describe reality. There is also a more extreme scenario that cannot yet be ruled out. If dark energy grows stronger over time instead of remaining constant, expansion could eventually overwhelm gravity even on smaller scales. Galaxy clusters would be pulled apart. Galaxies themselves would dissolve. Star systems, planets, molecules, and eventually atoms could be torn apart in a hypothetical future known as the Big Rip. Current data does not favour this outcome, but uncertainties remain. Measuring dark energy precisely is extraordinarily difficult, and small changes in its behaviour could have enormous long-term consequences. What is already clear is that dark energy dominates the cosmos. It stretches space, hides vast regions of reality beyond our reach, and determines what future observers will be able to see. It is the reason the observable universe spans 93 billion light-years. It is the reason most of existence will forever remain invisible. And yet, dark energy alone does not explain the universe we observe. Because while it pulls space apart on the larger scales, something else must pull matter together on smaller ones. Something must counter expansion locally, allowing galaxies to form, clusters to grow, and structure to emerge instead of dissolving into uniform fog. That force is equally invisible, equally mysterious, and absolutely essential. To understand how the universe holds itself together even as it expands, we have to turn to the unseen framework that shapes every galaxy, every cluster, and every filament of the cosmic web. If dark energy governs how the universe expands, then dark matter governs how it holds itself together. Without it, the universe revealed by the James Webb Space Telescope would not exist in any recognizable form. Galaxies would never have assembled, clusters would have flown apart, and the vast filamentary structure stretching across the cosmos would have remained a nearly uniform fog of matter. Dark matter does not shine, it does not absorb light, it does not emit radiation of any kind we can directly detect. And yet, it outweighs everything we can see by more than 5 to 1. Roughly 85% of all matter in the universe is dark matter, detectable only through its gravitational influence. Every star, planet, nebula, and galaxy is built within a framework dominated by something fundamentally invisible. The first clues to its existence emerged nearly a century ago, when astronomers noticed that galaxies were behaving in ways that made no sense. Stars in the outer regions of spiral galaxies were orbiting far too fast. According to the gravity generated by visible matter alone, those stars should have been flung into intergalactic space. Instead, they remained bound, moving as if each galaxy were embedded in a massive unseen halo. That unseen mass was dark matter. As observations expanded, the evidence became impossible to ignore. Entire galaxy clusters showed the same problem on much larger scales. Individual galaxies within clusters moved too quickly to be held together by stars and gas alone. Gravitational lensing revealed distortions in background galaxies far stronger than visible matter could produce. Again and again, the conclusion was unavoidable. Most of the universe's matter is invisible. What makes dark matter so important is not just how much of it exists, but how it behaves. Unlike ordinary matter, dark matter does not collide with itself or lose energy by emitting radiation. It passes through space almost frictionlessly. This allowed it to begin clumping extraordinarily early in cosmic history. Shortly after the Big Bang, the universe was nearly uniform, with tiny density fluctuations imprinted during its earliest moments. Dark matter responded to those fluctuations first. While ordinary matter remained hot and resisted collapse, dark matter quietly gathered into growing concentrations, forming massive invisible halos long before the first stars ignited. These halos became the scaffolding of the universe. As the universe cooled, ordinary matter began falling into these dark matter wells. Gas collected, compressed, and eventually ignited nuclear fusion. Stars formed, galaxies assembled. Not randomly, but precisely where dark matter had already gathered. The visible universe traces an invisible blueprint laid down billions of years earlier. This process produced one of the most striking features of reality, the cosmic web. On the larger scales, matter is arranged in vast filaments stretching tens to hundreds of millions of light-years across. These filaments intersect at dense nodes where galaxy clusters form. Between them lie enormous voids, regions so empty they contain almost no galaxies at all. This structure is not artistic coincidence. It is the natural outcome of gravity acting on dark matter over cosmic time. James Webb's observations have brought this architecture into sharper focus than ever before. By cataloguing hundreds of thousands of galaxies and measuring their distances, astronomers can map the three-dimensional distribution of matter across the universe. The pattern is unmistakable. Galaxies line up along filaments, they cluster at intersections, they are void of vast empty regions. The visible universe follows an invisible skeleton. What makes Webb especially powerful is its ability to see through dust and detect faint, distant galaxies that previous surveys missed. This fills in gaps in the cosmic web, revealing how early these structures emerged. Webb has shown that filaments were already well established when the universe was only a few billion years old, and that matter was flowing along them into growing clusters. This flow is not just a metaphor. Simulations and observations indicate that gas streams along dark matter filaments, like traffic along cosmic highways. Galaxies grow not only by forming stars internally, but by continuously accreting fresh material delivered along these invisible routes. Even our own galaxy participates in this process. The Milky Way resides on a filament connecting larger structures, drifting through space along pathways defined by dark matter. On these scales, motion is guided, not random. For decades, the role of dark matter in shaping the cosmic web rested largely on simulations and indirect evidence. But recently, astronomers achieved something remarkable. They detected dark matter directly along the filaments themselves. Using gravitational lensing, scientists measured how light from distant background galaxies was subtly distorted as it passed through regions where filaments were predicted to exist. The distortions were faint and difficult to detect, but consistent. They revealed mass where no visible matter could account for it. Dark matter was not just concentrated in clusters, it was stretched across space, threading the universe together. This transformed the cosmic web from a theoretical construct into an observed structure. The universe is not a loose collection of galaxies drifting apart. It is an interconnected network, shaped and sustained by invisible matter. The nodes of this network are galaxy clusters, the most massive gravitationally bound objects in existence. A single cluster can contain hundreds or thousands of galaxies, along with vast reservoirs of superheated gas and enormous quantities of dark matter. These clusters act as anchors, pulling matter along filaments toward their centers. When galaxies fall into clusters, they experience dramatic changes. The dense environment strips away gas, shuts down star formation, and reshapes galactic structure. James Webb has captured these transformations in detail, showing galaxies mid-transition as they are altered by their surroundings. The cosmic web is not static. It is active, dynamic, and constantly reshaping the universe. Yet for all its influence, dark matter remains one of the greatest mysteries in physics. We still do not know what it is made of. It may consist of unknown particles beyond the standard model. It may involve entirely new physics. Despite decades of experiments, dark matter has never been directly detected in a laboratory. And still, its presence is undeniable. Every galaxy rotation curve, every lensing map, every large-scale structure survey points to the same conclusion. Remove dark matter from the equations, and the universe we observe simply cannot exist. James Webb does not solve the dark matter mystery, but it strengthens the case for its central role. By revealing how quickly structure formed in the early universe, Webb shows that visible matter alone could never have done the job. Dark matter provided the gravitational head start needed to assemble galaxies just a few 100 million years after the Big Bang. It also explains why the universe looks the way it does today. The vast emptiness of cosmic voids, the dense richness of clusters, and the filamentary bridges connecting them all emerge naturally when dark matter dominates gravity. Yet even this invisible framework operates within a universe being pulled apart by dark energy. Dark matter builds structure. Dark energy stretches space. The universe exists in a constant tension between these two unseen forces. On smaller scales, gravity wins, galaxies form, clusters grow. On the larger scales, dark energy prevails, driving galaxies apart and pushing regions of space beyond our cosmic horizon. James Webb has shown us that the universe is not merely larger than expected. It is more organized, more interconnected, and more dependent on invisible forces than we ever imagined. What we see, stars, galaxies, nebulae, is only the illuminated surface of a far deeper structure, an unseen architecture holding reality together. And when we step back far enough to consider that structure as a whole, another realization becomes unavoidable. Even this vast, interconnected universe is only what we can observe from our position in space and time. Beyond it, the universe continues, shaped by the same invisible forces, unfolding beyond any horizon we can ever cross. If you like the video, don't forget to leave a like and subscribe. It makes a huge difference and helps the channel grow.